Tonight, we're going to talk about something that changes everything we thought we knew about finding life in the universe. For decades, scientists have been searching for planets like Earth, worlds with liquid water, breathable atmospheres, and stable temperatures. We've been looking for Earth's twin, assuming that the best place for life would be a planet almost identical to our own. But we were wrong. The thousands of exoplanets we've discovered have revealed something unexpected. The most common, potentially habitable worlds in the galaxy are nothing like Earth. They're bigger, orbiting different types of stars, some tidally locked with one side in permanent daylight. And here's the remarkable part. These differences aren't disadvantages. Scientists studying these worlds have realized that many of them could be even more suitable for life. By the end of tonight, you're going to see why the search for alien life is no longer about finding Earth's twin, and why the most habitable planets in the universe might be worlds we never expected. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. To understand why we've been looking in the wrong places, we need to start with Earth itself. Our planet sits in what astronomers call the habitable zone, sometimes called the Goldilocks zone. It's the region around a star where temperatures are just right for liquid water to exist on a planet's surface. Not too hot that water boils away, not too cold that it freezes solid. Earth orbits the Sun at an average distance of 93 million miles, or 150 million kilometers. At this distance, our planet receives enough energy to maintain average surface temperatures around 59 degrees Fahrenheit or 15 degrees Celsius. This is perfect for liquid water, which covers roughly 71% of Earth's surface. Water is essential for life as we know it. It's a solvent that allows chemical reactions to occur. It transports nutrients and waste products in living organisms. It moderates temperature through evaporation and freezing. Without liquid water, the complex chemistry that powers life simply can't happen. So for years, the search for habitable planets focused on finding Earth analogues. Planets roughly the same size as Earth, orbiting Sun-like stars at roughly the same distance we orbit the Sun. The logic seems sound. Life emerged on Earth, so planets like Earth must be the best places for life. This assumption shaped our entire approach to astrobiology. When we built planet-hunting telescopes, we optimized them to find Earth-sized worlds. When we calculated which stars to search around, we focused on stars similar to the Sun. When we talked about potentially habitable worlds, we described them in terms of how Earth-like they were. The more similar to Earth, the more promising the planets seemed. But this Earth-centric view came from a fundamental limitation. We had a sample size of exactly one planet with life, Earth. One star that we knew could support a living world. The Sun, one type of planetary system that had produced biology, ours. It's like trying to understand what makes a good home for humans when you've only ever seen one house. You might conclude that all houses must have exactly the same layout, the same materials, the same design as that single example. But once you see more houses, you realize there are countless ways to create a comfortable living space. The same turned out to be true for habitable planets. The search for exoplanets, planets orbiting other stars, began in earnest in the 1990s. Before then, we had theories about planets around other stars, but no concrete evidence. We knew our solar system existed, but we didn't know if planetary systems were common or rare. Then, in 1995, astronomers Michel Mayor and Didier Queloz announced the discovery of 51 Pegasi b. It was the first confirmed exoplanet orbiting a sun-like star, and it was nothing like anyone expected. 51 Pegasi b is a gas giant roughly half the mass of Jupiter, but it orbits its star at a distance of just 4.8 million miles or 7.7 million kilometers. That's closer than Mercury is to the Sun, completing one orbit every 4 days. This planet shouldn't exist according to our theories at the time. Giant planets were supposed to form far from their stars, where it's cold enough for ice to condense. But 51 Pegasi b was orbiting so close that temperatures reached around 1,800 degrees Fahrenheit, or 980 degrees Celsius. The discovery forced astronomers to rethink everything. It turned out that giant planets could migrate inward after forming, and planetary systems could be wildly different from our own. This was just the beginning. Since then, we've discovered over 5,400 confirmed exoplanets. The number grows almost monthly as new detection methods find more worlds. We've found planets larger than Jupiter, orbiting closer to their stars than Mercury. We've found planets orbiting binary star systems. We've found rogue planets drifting through space with no star at all. We've found systems with 7 Earth-sized planets packed tightly around a single star. The universe's creativity in assembling planetary systems far exceeds what we imagined. Among all these exotic worlds, one category stands out as particularly common and particularly interesting for the search for life. They're called super-Earths. A super-Earth is defined as a planet with a mass between Earth's and Neptune's. That's a wide range, from 1 Earth mass up to about 17 Earth masses. In terms of radius, super-Earths are typically between 1.2 and 2 times Earth's diameter. These planets don't exist in our solar system. We have Earth with a mass of 1, and we have Neptune with a mass of 17. Nothing in between. This created a blind spot in our understanding. Because we didn't have a super-Earth in our own system, we didn't think much about what such planets might be like. But it turns out that super-Earths are the most common type of planet in the galaxy. Surveys of exoplanets show that roughly 30 to 50% of Sun-like stars have at least one super-Earth. They're everywhere. The Kepler Space Telescope, which operated from 2009 to 2018, revolutionized our search for these worlds. It stared at a patch of sky containing about 150,000 stars and watched for tiny dips in starlight caused by planets passing in front of their stars. Over its mission, Kepler discovered over 2,600 confirmed planets, and a huge fraction of these discoveries were super-Earths. They weren't just common, they were the dominant type of planet in the habitable zones of their stars. And among these thousands of discovered super-Earths, we've found worlds that could change everything we thought we knew about where to look for life. The first one takes us back to where our search for Earth-like worlds really began. Kepler 452b was discovered in 2015, and when the announcement came, it made headlines around the world. Scientists called it Earth's cousin. This planet orbits a sun-like star about 1,400 light-years from Earth. The star, Kepler 452, is only slightly larger and brighter than our Sun. It's about 1.04 times the Sun's mass, and about 20% more luminous. Most importantly, it's about 6 billion years old, 1.5 billion years older than the Sun. This matters because it means the planet has had an enormous amount of time for life to develop. On Earth, life emerged within the first billion years after the planet formed. Simple single-celled organisms appeared around 3.8 billion years ago. For the next 3 billion years, life remained simple, bacteria, archaea, and eventually single-celled eukaryotes. Then about 600 million years ago, complex multicellular life exploded onto the scene. The Cambrian explosion saw the rapid diversification of animal forms. From that point forward, life became increasingly complex. Fish, land plants, insects, reptiles, mammals, birds, and eventually humans. The entire journey from simple cells to technological civilization took about 4 billion years. Kepler 452b has had 6 billion years. If life emerged there as quickly as it did on Earth, it would have had an extra 2 billion years to evolve. 2 billion years is an enormous amount of time. 2 billion years ago on Earth, life was still entirely single-celled. No plants, no animals, no fungi, just bacteria and archaea in the oceans. The leap from single cells to complex life took all that time. On Kepler 452b, if evolution followed a similar pace, complex life could have emerged 4 billion years ago. That's when Earth was still in its Hadean or early Archean eons, being bombarded by asteroids. Any life on Kepler 452b would have had 4 billion years to become sophisticated, to develop ecosystems as complex as Earth's rainforests or coral reefs, to potentially evolve intelligence, to possibly develop civilization and technology. This is pure speculation, of course. We don't know if life exists there at all, but the possibility is tantalizing. Kepler 452b has a radius about 1.6 times Earth's. This makes it a super-Earth, just barely larger than the cutoff between Earth-sized and super-Earth classifications. The exact boundary is somewhat arbitrary. Most astronomers use 1.6 Earth radii as the upper limit for rocky planets. Above that size, planets tend to accumulate thick hydrogen atmospheres and become mini-Neptunes. Kepler 452b is right at that boundary. Based on its size, scientists estimate it has about 5 times Earth's mass. If it's rocky, which seems likely given its size, it would have stronger gravity than Earth, about 1.6 times stronger at the surface. Standing on Kepler 452b, if you weigh 150 pounds on Earth, you'd weigh about 240 pounds there. That's significant, but not prohibitive for life. Organisms would evolve stronger muscles and sturdier skeletons. They'd be built for the higher gravity from the start, and in exchange for the higher gravity, they'd get several advantages. More internal heat from radioactive decay. A planet with 5 times Earth's mass has 5 times as much uranium, thorium, and potassium in its interior. These elements decay and produce heat. More heat means more vigorous plate tectonics, faster recycling of materials between the surface and interior, better long-term climate regulation. The planet could maintain habitable temperatures for far longer than Earth can. Earth will become uninhabitable in about 1 to 2 billion years as the sun continues to brighten. Eventually, the increasing solar energy will trigger a runaway greenhouse effect. The oceans will evaporate, water vapor will trap more heat, and Earth will become a second Venus. Kepler 452b's star is also brightening with age. But the planet's more vigorous geology would help it compensate. Increased weathering of rocks would remove carbon dioxide from the atmosphere faster. reduced greenhouse effect would cool the planet. The planet could maintain balance for much longer than Earth, perhaps an additional 1 billion or 2 billion years of habitability beyond what Earth will have. Here's what makes this planet so remarkable. It orbits in the habitable zone at a distance of about 103 million miles or 166 million kilometers from its star. Its orbital period is 385 days. 385 days. That's almost exactly 1 Earth year. This planet experiences seasons, a calendar year, and day-night cycles in ways that are eerily similar to Earth. If the planet has an axial tilt, like Earth's 23.5 degrees, it would have seasons: summer and winter, spring and fall. The changing angle of sunlight would drive seasonal temperature variations. Plant life, if it exists, might have seasonal growth cycles. Animals might migrate or hibernate. Civilizations, if they exist, might have developed agriculture timed to the seasons. The similarities to Earth are profound, but so are the differences. The planet is 25% larger in radius. That means about 56% more surface area. If half the surface is land, like Earth, that's 56% more land area. More space for ecosystems, more room for biodiversity, more territory for civilizations to develop. The increased surface area also affects climate. More surface means more variation in geographical features. Larger continents, larger ocean basins, larger mountain ranges. Weather systems might be more complex than Earth's. The planet receives about 10% more energy from its star than Earth receives from the Sun. This places it near the inner edge of the habitable zone, slightly warmer than Earth, but not too warm. Climate models suggest that with an Earth-like atmosphere, surface temperatures would be moderate, perhaps a bit warmer than Earth on average, but still well within the range for liquid water. Average temperatures might be around 65 to 70 degrees Fahrenheit, or 18 to 21 degrees Celsius, compared to Earth's current average of about 59 degrees Fahrenheit, or 15 degrees Celsius. Warmer, but not drastically so. The poles might have less ice, or no permanent ice caps at all. The tropics might be hotter, perhaps approaching the upper limits of what complex life can tolerate. But the temperate zones would be expansive and pleasant, ideal for forests, grasslands, and potentially agriculture. If this planet has plate tectonics, it would be more vigorous than Earth's. More volcanic activity, faster movement of tectonic plates, more mountain building. This has pros and cons. More volcanism means more nutrients cycling from the interior to the surface. Volcanic ash fertilizes soil, supporting plant growth. But it also means more frequent eruptions, which could be hazardous to life. Faster plate movement means more earthquakes. Mountain ranges would rise and erode more quickly. Coastlines would change more rapidly. Life would need to adapt to a more geologically active world. But Earth's life has already shown it can handle significant geological activity. The Pacific Ring of Fire hosts some of Earth's most biodiverse regions despite frequent earthquakes and eruptions. Ecosystems near active volcanoes can be incredibly productive. The same would likely be true on Kepler 452b. If it has oceans, they might cover more of the surface than Earth's 71%. Perhaps 80% ocean, 20% land. This would create different climate dynamics. More ocean means more heat storage. Water has high heat capacity, It takes a lot of energy to warm it up or cool it down. An ocean-dominated planet would have very stable temperatures. Less seasonal variation, less day-to-night temperature change. This stability would be beneficial for life. The oceans would be teeming with marine ecosystems. Vast expanses of open water supporting plankton blooms, coral reefs, or their alien equivalents in shallow coastal waters. Deep ocean trenches hosting vent ecosystems. Migratory species traveling thousands of miles between feeding and breeding grounds. The 20% land area would be precious. Continents might be smaller and more fragmented than Earth's. Island chains, archipelagos, peninsulas. This fragmentation could drive speciation. Populations isolated on different islands would evolve independently. Over millions of years, you'd get a vast diversity of species. Similar to how islands on Earth, like the Galapagos, have unique species found nowhere else. The planet is too far away for us to study its atmosphere with current technology. At 1,400 light-years, the starlight is too faint for detailed spectroscopy with existing instruments. Even the James Webb Space Telescope, powerful as it is, can't resolve fine details of atmospheres at that distance. But future telescopes could change that. The Habitable Worlds Observatory, planned for the 2040s, is specifically designed to study planets like this. It would have the sensitivity to detect and analyze light from planets around distant, sun-like stars. For Kepler 452b, the observatory would look for reflected light. The planet doesn't emit much light of its own, it's not hot enough, but it reflects its star's light, and that reflected light contains information. Different molecules in the atmosphere absorb different wavelengths. Oxygen absorbs in the visible spectrum, creating a distinctive pattern. Water vapor absorbs in the near-infrared. Methane absorbs in specific infrared bands. By analyzing the spectrum of reflected light, we can determine what gases are present. If we detected oxygen and methane together in significant quantities, it would be compelling evidence for biological activity. On Earth, these gases coexist only because life continuously produces them. Oxygen from photosynthesis, methane from biological decay and metabolic processes. Without life maintaining them, they would react chemically and disappear from the atmosphere within a few million years. So finding both together would strongly suggest life. Not proof, there might be non-biological ways to produce both gases, but strong evidence that would warrant further investigation. If we detected chlorophyll or similar photosynthetic pigments, it would be even stronger evidence. Chlorophyll has a distinctive spectral feature called the red edge. It reflects strongly in near-infrared wavelengths, just beyond the red part of the visible spectrum. This creates a sharp increase in reflectivity that's visible in spectroscopic data. Detecting the red edge on an exoplanet would indicate photosynthetic life covering significant portions of the surface. Not bacteria or simple algae, but complex plant life or their alien equivalents. Forests, grasslands, photosynthetic organisms on a planetary scale. And if we detected industrial pollutants, nitrogen dioxide, or fluorinated gases, it would suggest technological civilization. These gases don't occur naturally in planetary atmospheres. They're produced by combustion, industrial processes, or refrigeration. Finding them would mean someone is manufacturing them. An intelligent species with technology. The significance of Kepler 452b goes beyond this single planet. It's proof of concept. Before its discovery, We knew theoretically that planets could exist around sun-like stars in habitable zones, but we hadn't found many examples. Most early exoplanet discoveries were hot Jupiters, giant planets orbiting very close to their stars. These are easier to detect because they're large and cause bigger signals. Finding Earth-sized or super-Earth-sized planets around sun-like stars at Earth-like distances is much harder. The signals are smaller, the orbital periods are longer, and you need years of observations to confirm them. Kepler 452b proved it's possible. Not just theoretically possible, but actually exists in nature. A super-Earth, larger than our planet, but still potentially rocky, orbiting a sun-like star at a distance that allows liquid water, with a year almost identical to Earth's. If we found one, there are probably millions more, maybe billions. But Kepler 452b isn't the only super-Earth that might be more habitable than our planet. In fact, recent statistical analysis has identified an even more promising candidate. Kepler 22b was discovered in 2011, 4 years before Kepler 452b. It was actually the first planet Kepler found in the habitable zone of a sun-like star. And, in 2025, a comprehensive study analyzing 517 exoplanets using 8 different planetary and stellar parameters concluded that Kepler 22b is the most Earth-like planet we've discovered. The most habitable world we know of beyond our solar system. Kepler 22b orbits a star about 600 light-years from Earth. The star, Kepler 22, is slightly smaller and cooler than the Sun. It has about 97% of the Sun's mass and about 79% of the Sun's luminosity. The planet has a radius about 2.4 times Earth's. This makes it significantly larger than Kepler 452b. We don't know its exact mass because it was discovered using the transit method, which only reveals the planet's size, not its mass. But based on models of planetary composition, it likely has a mass somewhere between 10 and 36 times Earth's mass. If it's on the lower end of that range, it's probably a rocky super-Earth with a thick atmosphere. If it's on the higher end, it might be a mini Neptune with a substantial hydrogen envelope. Most scientists think it's probably somewhere in the middle, a super-Earth with a rocky core and a thick but not overwhelming atmosphere. What makes Kepler 22b stand out is its orbital characteristics. It orbits its star every 290 days, at a distance of about 84 million miles or 136 million kilometers. This places it squarely in the middle of the habitable zone, right in the sweet spot where temperatures are most favorable for liquid water. Not too close like Kepler 452b, which is near the inner edge. Not too far like some other candidates that are near the outer edge, right in the center. The planet receives about 25% less energy from its star than Earth receives from the Sun. This might sound like it would be too cold, but remember, the planet is likely larger than Earth, with a thicker atmosphere. A thicker atmosphere means more greenhouse warming. Climate models suggest that with a carbon dioxide-rich atmosphere, similar to what Earth had early in its history, Kepler 22b could have average surface temperatures around 72 degrees Fahrenheit or 22 degrees Celsius. Warmer than Earth's current average, but well within the range that life could tolerate. If the planet has less carbon dioxide and more nitrogen and oxygen, like modern Earth, temperatures might be slightly cooler. Perhaps around 50 to 60 degrees Fahrenheit, or 10 to 15 degrees Celsius. Still perfectly habitable. The statistical study that identified Kepler-22b as the most Earth-like planet looked at 8 key factors: planetary radius, orbital period, stellar temperature, stellar radius, distance from the star, the planet's equilibrium temperature, and the star's metallicity. When all these factors were weighted and compared, Kepler-22b came out on top. It's not identical to Earth, no exoplanet is, but it's the closest match we've found so far. If Kepler-22b is rocky, which seems probable, it would have advantages over Earth in several ways. Its larger size means more geological activity, more volcanism, more plate tectonics, better long-term climate stability. Its larger size also means a stronger magnetic field that lasts longer, better protection from its star's radiation. Its position in the center of the habitable zone gives it a buffer against changes in the star's luminosity. As Kepler-22 ages and brightens over billions of years, the planet would remain comfortably habitable even as the habitable zone shifts outward. Earth, by contrast, is already approaching the inner edge of the Sun's current habitable zone. In another billion years, Earth might be too hot for complex life. Kepler-22b has billions of years more than that before it faces similar problems. There's also the question of what the surface might look like. If the planet is entirely covered by ocean, which is possible given its likely high water content, it might have a global ocean hundreds of miles deep. This ocean would be teeming with life if biology emerged there. Marine ecosystems covering the entire planet, possibly more diverse and productive than Earth's oceans. If the planet has continents, they would be larger than Earth's continents. Simply because the planet is larger, more land area means more ecological niches, more opportunities for evolution to experiment. We won't know for certain what Kepler-22b is like until we can study it directly, but the statistical analysis gives us confidence that this is one of the best targets for future observations. When the Habitable Worlds Observatory launches in the 2046, Kepler-22b will almost certainly be near the top of the observation list. If any exoplanet is going to show us signs of life, this might be the one. While Kepler-452b and Kepler-22b represent super-Earths around Sun-like stars, the most abundant, potentially habitable worlds orbit a very different type of star. TRAPPIST-1 is an ultra-cool red dwarf located about 40 light-years from Earth. It has only about 9% of the Sun's mass and is incredibly dim, putting out only about 0.05% of the Sun's luminosity. What makes TRAPPIST-1 extraordinary is its planetary system. It has 7 Earth-sized planets, all packed tightly around the star. The entire system could fit inside Mercury's orbit around the Sun. The 7 planets are designated TRAPPIST 1b through H. 3 of them, planets E, F, and G, are in the habitable zone. This is the only known system with multiple potentially habitable planets. TRAPPIST-1e is particularly intriguing. It has a radius, about 92% of Earth's, and likely has a rocky composition. It orbits at a distance of about 2.3 million miles, or 3.7 million kilometers, completing one orbit every 6.1 days. At this distance, it receives about 60% as much energy from its star as Earth receives from the Sun. Climate models suggest that with an Earth-like atmosphere, TRAPPIST-1e could have surface temperatures suitable for liquid water. It might be covered partly or entirely by oceans. If it has active geology, it could have continents and plate tectonics. It could, in principle, be a world very much like Earth, just orbiting a much dimmer, cooler star at a much closer distance. The planet is almost certainly tidally locked, with one side always facing the star. But, as we discussed earlier, this doesn't preclude habitability. Atmospheric circulation would distribute heat, preventing extreme temperature gradients. There could be a stable climate pattern with moderate temperatures across large regions of the planet. TRAPPIST-1F is slightly larger, with a radius about 4% bigger than Earth's. It receives about 38% as much energy as Earth. With a significant greenhouse atmosphere, particularly one rich in carbon dioxide, the planet could maintain liquid water on its surface. It might be a colder world than Earth, with ice caps and possibly a global frozen ocean, except in regions warmed by volcanic activity or in the subsolar region. TRAPPIST-1G is even farther out, receiving about 23% of Earth's solar energy. It's at the outer edge of the habitable zone, colder still. But with the right atmosphere, it could have liquid water in some regions, particularly if geological activity provides additional heat. One of the most exciting aspects of the TRAPPIST-1 system is that these planets are ideal targets for atmospheric characterization. When a planet transits its star, some of the starlight passes through the planet's atmosphere. Different atmospheric gases absorb specific wavelengths of light, creating a unique spectral fingerprint. By analyzing this, we can determine what gases are present. The James Webb Space Telescope is currently observing TRAPPIST-1 planets during transits. The goal is to detect gases like water vapor, carbon dioxide, methane, and oxygen. Some of these gases, particularly oxygen and methane in combination, could be biosignatures. On Earth, oxygen is produced by photosynthetic life, and methane is produced by both biological and geological processes. If we detected both in significant quantities in an exoplanet's atmosphere, it would be compelling evidence for biological activity. Initial observations have been challenging. The first observations of TRAPPIST-1b showed that it likely doesn't have a thick atmosphere. But observations of the other planets, particularly E, F, and G, are ongoing. If we can confirm that planets like TRAPPIST-1e have atmospheres with water vapor, it would be a major step forward. It would confirm that these potentially habitable worlds actually have the conditions necessary for life as we know it. The TRAPPIST-1 system represents a new category of habitable worlds, not Earth-sized planets around sun-like stars, but Earth-sized planets around red dwarfs. These systems are far more common than sun-like systems. For every star like the Sun, there are about 3 red dwarfs. If most red dwarfs have planetary systems like TRAPPIST-1, with multiple rocky planets in their habitable zones, then the number of potentially habitable worlds in the galaxy is staggering. Billions upon billions of planets where life could exist. The TRAPPIST-1 system might be our first real glimpse of what most habitable worlds in the universe actually look like. Even closer to home, just 4 light-years away, we have another potentially habitable world. Proxima Centauri is the closest star to our solar system. It's a red dwarf, smaller and dimmer than the Sun, with about 12% of the Sun's mass. In 2016, astronomers announced the discovery of Proxima Centauri, b. This planet has a minimum mass of about 1.3 Earth masses, making it either a large Earth or a small super-Earth. It orbits at a distance of about 4.6 million miles, or 7.5 million kilometers, completing one orbit every 11.2 days. At this distance, the planet receives about 65% as much energy from its star as Earth receives from the Sun. This places it squarely in the habitable zone. Temperature estimates suggest that with an Earth-like atmosphere, surface temperatures could be in the range suitable for liquid water. The planet is almost certainly tidally locked, but climate models show this doesn't prevent habitability. What makes Proxima Centauri b especially interesting is its proximity. 4.24 light-years is nothing in astronomical terms. Light from Proxima Centauri that we see tonight left the star 4 years ago. If we launched a spacecraft today at current speeds, it would take about 6,000 years to reach Proxima Centauri. But proposed future technologies could change that dramatically. The Breakthrough Starshot initiative is exploring the possibility of building gram-scale spacecraft with light sails. These tiny probes would be accelerated using ground-based lasers to 20% of the speed of light. At that speed, a probe could reach Proxima Centauri in about 20 years. If Proxima Centauri b is habitable, or even if it has life, we might be able to get direct images within a few decades. Not by traveling there ourselves, but by sending robotic explorers at relativistic speeds. This makes Proxima Centauri b not just scientifically interesting, but practically accessible in ways that more distant systems aren't. However, there are concerns about the planet's habitability. Red dwarfs, especially small ones like Proxima Centauri, are prone to violent stellar flares. These are sudden bursts of energy and charged particles much more powerful than anything the Sun produces. Proxima Centauri experiences regular flares that increase its brightness by factors of several times. During a major flare, the planet would be bathed in ultraviolet and X-ray radiation. Over time, this radiation could strip away the planet's atmosphere and sterilize the surface. But there are potential mitigations. A strong magnetic field would deflect much of the harmful radiation. A thick atmosphere could absorb the radiation before it reaches the surface. Life could exist in oceans, protected by water, or underground, shielded by rock. And flare activity decreases as red dwarfs age. Proxima Centauri is about 4.85 billion years old, roughly the same age as the Sun. It might have passed through its most active phase and entered a calmer period. If Proxima Centauri b has maintained its atmosphere and magnetic field, it could be habitable despite the stellar flares. The planet represents our best near-term opportunity to study a potentially habitable world in detail. Future telescopes might be able to directly image it, separating its light from the star's light. We could analyze that light spectroscopically, determining what gases are in its atmosphere. We could look for biosignatures. We could search for signs of technological civilization, all from a planet just 4 light-years away. Proxima Centauri b is a reminder that the search for life doesn't require looking across vast cosmic distances. The nearest potentially habitable planet is practically in our cosmic backyard. Another remarkable discovery takes us to a triple star system, 22 light-years from Earth. Gliese 667. C is a red dwarf, part of a system with 2 other stars. It's about 1/3 the mass of the Sun and much dimmer. In 2011 and 2012, astronomers announced the discovery of multiple planets orbiting this star. One of them, Gliese 667 cc, quickly became one of the most talked about potentially habitable worlds. Gliese 667 cc has a minimum mass of about 3.8 Earth masses. This makes it a definite super-Earth. It orbits in the habitable zone at a distance of about 12 million miles or 20 million kilometers from its star. Its orbital period is 28 days. The planet receives about 90% as much energy from its star as Earth receives from the Sun. This is remarkably similar to Earth's energy budget. Climate models suggest that with an Earth-like atmosphere, the planet could have temperatures very similar to Earth's. Average surface temperatures might be around 55 to 65 degrees Fahrenheit, or 13 to 18 degrees Celsius. Comfortable, moderate, potentially perfect for life. Like most planets in red dwarf habitable zones, Gliese 667c is probably tidally locked, but its relatively high energy input means atmospheric circulation would be vigorous. Heat would be distributed efficiently from day side to night side. Both hemispheres could have liquid water. What makes this planet particularly intriguing is the stellar system it's part of. Gliese 667c has two companion stars, Gliese 667 A and B. These are a binary pair, orbiting each other at a distance of about 12 astronomical units. Gliese 667c orbits this binary pair at a much larger distance, about 230 astronomical units. From the perspective of someone standing on Gliese 667cc, the sky would be extraordinary. The red dwarf star it orbits would appear large and reddish, dominating the day-side sky. But in the night sky, the two companion stars would be visible as bright points of light, much brighter than any star in Earth's night sky, bright enough to cast shadows, bright enough to read by. This triple star system creates a unique environment that doesn't exist anywhere in our solar system. The planet receives not just light and warmth from its primary star, but also additional light from the two companion stars. This extra illumination might affect the planet's climate in subtle ways. It might allow photosynthesis on the night side, powered by the light from the companion stars rather than the primary star. It might create interesting ecological niches where life adapts to different light conditions. The discovery of Gliese 667cc demonstrated that habitable planets can exist in complex stellar systems. We don't need a lone sun-like star to have potentially habitable worlds. Even in systems with multiple stars, planets can find stable orbits in habitable zones. This expands the number of potential homes for life. Not just planets around single stars, but planets in binary and triple star systems as well. However, there's some uncertainty about Gliese 667cc. Like many early exoplanet discoveries detected using the radial velocity method, some researchers have questioned whether the signal is real or an artifact. Follow-up observations are ongoing. If the planet is confirmed, it will remain one of the most Earth-like super-Earths we've found. If it turns out to be a false positive, it's a reminder that exoplanet detection is challenging and requires careful verification. But the principle remains. Super-Earths in the habitable zones of red dwarfs are common, and some of them orbit in complex stellar systems that would create environments unlike anything in our solar system. Beyond these headline discoveries, dozens of other super-Earths in habitable zones have been found. LHS 1140b, located about 49 light-years or 290 trillion miles from Earth, is a super-Earth with about 6.6 times Earth's mass. It orbits in the habitable zone of its red dwarf star every 24.7 days. What's special about this planet is that observations with the Hubble Space Telescope detected signatures of a substantial atmosphere. The planet has retained its air despite orbiting close to its star. This suggests it has strong enough gravity and possibly a strong enough magnetic field to hold onto its atmosphere over billions of years. Follow-up observations with the James Webb Space Telescope are providing more details about the atmospheric composition. If water vapor is confirmed, it would be strong evidence that the planet could have liquid water on its surface. K2-18b. About 124 light-years, or 730 trillion miles away, made headlines in 2019 when astronomers detected water vapor in its atmosphere. This was the first time water vapor had been detected in the atmosphere of a planet in the habitable zone. The planet has a mass of about 8.6 times Earth's and a radius about 2.6 times Earth's. It orbits in the habitable zone, receiving about the same amount of energy from its star as Earth receives from the Sun. The presence of water vapor doesn't necessarily mean the planet has oceans. The planet's size suggests it might be a mini Neptune with a thick hydrogen atmosphere and no solid surface. But in 2023, astronomers announced the detection of carbon dioxide and methane in K2-18b's atmosphere as well. This raises the intriguing possibility that the planet might be a Hycean world. Hycean stands for hydrogen and ocean. These are hypothetical planets with global oceans covered by thick hydrogen atmospheres. The pressure from the atmosphere would keep the ocean liquid even at relatively low temperatures. Life in such an ocean would be very different from life on Earth's surface. It would exist under constant high pressure, possibly in complete darkness if the hydrogen atmosphere is opaque. But life might still be possible, using chemical energy instead of solar energy. Earth's deep oceans host ecosystems around hydrothermal vents that don't depend on sunlight. Life on a Hycean world might follow similar principles. Chemosynthetic bacteria could form the base of the food chain, converting chemical energy from volcanic vents into organic matter. Larger organisms could feed on these bacteria, creating complex ecosystems in the eternal darkness. The high-pressure environment would require special adaptations. Proteins would need to resist denaturation under pressure. Cell membranes would need to remain flexible despite the crushing weight of the atmosphere above. But Earth's deep-sea creatures have solved these problems, surviving at pressures hundreds of times higher than at the surface. If life can adapt to Earth's deep ocean, it can adapt to a Hycean world's high-pressure ocean. TOI 700c, discovered in 2021, is another promising candidate. This super-Earth has a mass of about 5 times Earth's and orbits in the habitable zone of its red dwarf star. It receives about 70% as much energy from its star as Earth receives from the Sun. Climate models suggest it could have moderate surface temperatures with the right atmosphere. The planet is part of a multi-planet system with at least 3 planets. Studying them together provides insights into how planetary systems form and evolve. Multi-planet systems are particularly interesting because the planets gravitationally interact with each other. These interactions can stabilize orbits, preventing planets from being ejected or crashing into the star. In some cases, the outer planets might protect inner habitable zone planets from comet and asteroid impacts. Just as Jupiter in our solar system deflects many potential impactors away from Earth, the outer planets in other systems might provide similar protection. This could make planets in multi-planet systems more hospitable to life by reducing the frequency of catastrophic impacts. Kepler 442b orbits a red dwarf about 1,200 light-years, or 7 quadrillion miles from Earth. It has a radius about 1.34 times Earth's and orbits in the habitable zone every 112 days. This is one of the longest orbital periods for any planet in a red dwarf's habitable zone. The long orbital period means the planet might not be fully tidally locked yet. It might experience day-night cycles just much longer than Earth's 24-hour day. Imagine a world where day lasts 56 days, followed by a night that lasts another 56 days. The climate would be unlike anything on Earth. During the long day, the sunlit hemisphere would heat up gradually. Oceans would warm, ice would melt, and weather patterns would intensify. During the long night, the hemisphere would cool slowly. Frost might form, water might freeze, and different weather patterns would emerge. But the atmosphere would circulate between day and night, moderating the extremes. The result might be a planet with dramatic seasonal variations, but still habitable conditions overall. Life on such a world would need to adapt to these long cycles. Plants might have different strategies for the long day and long night. Animals might migrate between hemispheres, following the moving terminator, where conditions are moderate. Or life might remain primarily in the oceans, where temperature variations are smaller and the long day-night cycles matter less. This planet demonstrates that there's a wide range of possible configurations for habitable super-Earths. Not all of them are tidally locked. Not all of them orbit tiny red dwarfs. The diversity is enormous, and each variation might offer unique advantages for life. Now, let's dig deeper into what makes super-Earths potentially more habitable than Earth itself. This might seem counterintuitive at first. Bigger planets have stronger gravity, which could make life more difficult. They might have thicker atmospheres, which could create a runaway greenhouse effect. They might be more geologically active, with more volcanism and earthquakes. These all sound like disadvantages. But it turns out that each of these factors, when present at the right level, actually enhances habitability rather than diminishing it. Understanding why requires looking at how planets work at a fundamental level. Super-Earths come in different varieties depending on their mass and composition. The smaller ones, those between 1 and about 1.5 Earth masses, are almost certainly rocky. They formed the same way Earth did, through the accumulation of solid material in the planet-forming disk around a young star. Dust particles collided and stuck together, growing into pebbles, boulders, kilometer-sized planetesimals, and eventually planet-sized bodies. These rocky super-Earths would have surfaces, atmospheres, and geological activity, potentially places where life could emerge. The larger super-Earths, those above about 1.6 Earth masses, might be something called mini-Neptunes. These worlds would have a rocky core, surrounded by a thick envelope of hydrogen and helium captured from the planet-forming disk. They might have gaseous atmospheres hundreds or thousands of miles deep, with no solid surface to stand on. The dividing line between rocky super-Earths and mini-Neptunes isn't perfectly clear. It depends on when and where the planet formed, how much gas was available, and how the planet's mass influenced its ability to hold on to that gas. But observations are starting to reveal which planets fall into which category. One technique involves measuring the planet's density. If we know a planet's mass from how it gravitationally tugs on its star, and we know its radius from how much starlight it blocks during a transit, we can calculate its density. Rocky planets like Earth have densities around 5.5 grams per cubic centimeter. That's because they're made of iron, nickel, and silicate rocks, all dense materials. Gas giants like Jupiter have densities around 1.3 grams per cubic centimeter, much lower because they're mostly hydrogen and helium, which are light elements. Super-Earths, with densities similar to Earth's, are almost certainly rocky. Those with much lower densities are probably mini-Neptunes. And what we're finding is that many super-Earths, in the habitable zones of their stars are rocky. They have the right density to be worlds with solid surfaces. This is extraordinarily important because it means these planets could potentially host life. The discoveries keep coming. Every year, we find more super-Earths in habitable zones. More worlds that could potentially host life. Each discovery refines our understanding of what makes a planet habitable. Each one adds to the statistical picture, showing that habitable worlds are common. But we're still in the early stages of characterizing these planets. We know they exist. We know their sizes and orbits. But we don't yet know what their atmospheres are like, or whether they actually have liquid water. That's changing with the James Webb Space Telescope and future missions. The James Webb Space Telescope, which began operations in 2022, is revolutionizing our ability to study exoplanet atmospheres. Unlike previous telescopes, Webb observes primarily in infrared wavelengths. This is crucial because many important atmospheric gases have strong absorption features in the infrared. Water vapor, carbon dioxide, methane, ammonia, all leave distinctive signatures in infrared spectra. Webb uses a technique called transit spectroscopy to study exoplanet atmospheres. When a planet passes in front of its star, some of the star's light filters through the planet's atmosphere before reaching us. Different gases in the atmosphere absorb different wavelengths. By measuring which wavelengths are absorbed, we can determine which gases are present. Webb has already observed several super-Earths using this technique. The results have been mixed but promising. Some planets show clear evidence of atmospheres with water vapor and carbon dioxide. Others appear to have no atmosphere at all, possibly stripped away by stellar radiation. Each observation teaches us something new about how super-Earth atmospheres behave. Over the next decade, Webb will observe dozens more potentially habitable super-Earths. The catalogue of atmospheric compositions will grow. We'll start to see patterns. Which types of super-Earths retain their atmospheres? Which ones have water vapor? Which ones have the right combination of gases to suggest biological activity? These questions will be answered through systematic observation. But Webb is just the beginning. Future telescopes will push even further. Ground-based observatories like the Extremely Large Telescope, currently under construction in Chile, will have mirrors over 100 feet, 30 meters, in diameter. That's more than 3 times larger than any existing telescope. The Extremely Large Telescope will be equipped with sophisticated instruments for direct imaging of exoplanets. It will use coronagraphs to block starlight and adaptive optics to compensate for atmospheric distortion. Now let's dig deeper into what makes super-Earths potentially more habitable than Earth itself. This might seem counterintuitive. Bigger planets have stronger gravity, which could make life more difficult. They might have thicker atmospheres, which could create a runaway greenhouse effect. They might be more geologically active, with more volcanism and earthquakes. These all sound like disadvantages. But it turns out that each of these factors, when present at the right level, actually enhances habitability rather than diminishing it. Let's start with geological activity. Earth's geology is powered by heat from 2 sources. First, leftover heat from the planet's formation. Second, heat from radioactive decay. Elements like uranium-238, thorium-232, and potassium-40 decay over time, releasing energy. This internal heat drives plate tectonics, the process by which Earth's outer shell is broken into pieces that move around. Plate tectonics is crucial for maintaining habitability on Earth. It recycles carbon between the atmosphere and the interior, acting as a thermostat for Earth's climate. If Earth gets too hot, weathering removes carbon dioxide faster, which cools the planet. If Earth gets too cold, volcanism continues releasing carbon dioxide, and the planet warms up. This feedback loop has kept Earth's temperature relatively stable for billions of years, despite the sun getting brighter over that time. Super-Earths have an advantage here. A planet with twice Earth's mass has more radioactive elements in its interior simply because it has more total material. This means more internal heat, more vigorous geological activity, and more efficient climate regulation. They could maintain stable temperatures through changes in their star's luminosity more effectively than Earth does. There's another advantage related to planetary magnetic fields. Earth has a strong magnetic field generated by convection in its liquid iron core. This magnetic field extends thousands of miles into space, creating a protective bubble called the magnetosphere. This magnetosphere deflects most of the solar wind, the stream of charged particles continuously flowing from the sun. Without this protection, the solar wind would gradually strip away Earth's atmosphere over hundreds of millions of years. Mars lost most of its atmosphere this way. Mars once had a magnetic field, but its smaller size meant it cooled faster. Its core solidified, the magnetic field disappeared, and the solar wind eroded Mars's atmosphere. Super-Earths, with their larger size and greater internal heat, would maintain active dynamos for longer periods. A super-Earth, with twice Earth's mass, might keep its magnetic field active for billions of years longer than Earth will. This extended magnetic protection would preserve the atmosphere and maintain habitable conditions for a much longer time. Think about what this means for the evolution of life. Life took about 500 million years to emerge on Earth after conditions became suitable. Then it took another 3 billion years for complex multicellular life to evolve. Then several 100 million more years for intelligence to emerge. A planet that can maintain habitable conditions for longer gives life more time to develop complexity. A super-Earth might have twice as much time for evolution to experiment and produce complex, possibly intelligent life. Now let's consider atmospheres. Earth's atmosphere has a surface pressure of 14.7 pounds per square inch, 1 bar in metric units. Super-Earths, with stronger gravity, would hold onto their atmospheres more tightly. Atmospheric gases are constantly trying to escape into space through a process called atmospheric escape. Earth loses atmosphere this way, but the rate is extremely slow. Super-Earths, with their stronger gravity, would have even lower escape rates. They could maintain substantial atmospheres over the entire lifetime of their stars. But there's a balance here. Too much gravity and the atmosphere becomes too thick, creating intense surface pressures. Too much atmospheric mass, and you get a runaway greenhouse effect. Venus is an example of this. Venus has roughly the same mass as Earth, but its atmosphere is 90 times thicker. The surface temperature is over 860 degrees Fahrenheit or 460 degrees Celsius. Super-Earths need to avoid this fate. They need enough atmosphere to have a climate system, but not so much that greenhouse warming becomes extreme. Within the habitable zone, a super-Earth can maintain a thick but stable atmosphere that enhances habitability rather than destroying it. A thicker atmosphere provides better insulation against temperature variations. It distributes heat more effectively across the planet. It provides more protection against radiation from space. All of these factors contribute to stability, and stability is crucial for life. Let's talk about water. Earth's surface is roughly 71% ocean, but a planet could easily be entirely covered by ocean if it had more water or less variation in crustal density. These are sometimes called ocean worlds. Super-Earths might be more likely to be ocean worlds than Earth. When planets form, they incorporate water from ices in the planet-forming disk. Beyond the frost line, the distance from the star where water ice can condense, there's abundant ice. In our solar system, the frost line is at about 3 astronomical units, roughly the distance of the asteroid belt. Inside this line, temperatures are too high for water ice to exist. Outside, ice is stable and can accumulate on growing planets. This is why the giant planets, Jupiter, Saturn, Uranus, and Neptune formed where they did. They grew large by accumulating ice along with rock and then capturing enormous amounts of gas. Earth formed inside the frost line, in the region too hot for water ice. So, where did Earth's water come from? Most likely from asteroids and comets that formed farther out and then migrated inward. These ice-rich bodies collided with Earth during its early history, delivering water to the surface. But this process is inefficient. Most of the water in asteroids and comets either vaporizes during impact or gets incorporated into rocks rather than staying on the surface. That's why Earth has relatively little water compared to its total mass. Only about 0.02%. If you collected all of Earth's water into a sphere, it would be only about 860 miles or 1,400 kilometers in diameter. Tiny compared to Earth's nearly 8,000-mile, 12,700 kilometer diameter. Super-Earths that form beyond the frost line and then migrate inward face a different situation. They form in ice-rich regions and accumulate vast amounts of water as they grow. When they migrate inward into the habitable zone, they bring this water with them. Unlike asteroids delivering water to Earth, the water is already incorporated into the planet's structure. It doesn't need to survive violent impacts. It's simply part of the planet from the beginning. A super-Earth formed this way might have water comprising 1%, 5%, even 10% of its total mass. If that water is mostly on the surface, you'd have a global ocean hundreds or even thousands of miles deep. To put this in perspective, Earth's deepest ocean point, the Mariana Trench, reaches about 7 miles or 11 kilometers deep. The average depth is about 2.3 miles or 3.7 kilometers. But a super-Earth ocean world might have oceans averaging 100 miles deep, 200 miles deep, or more. What would such an ocean be like? At the surface, it would look similar to Earth's oceans. Liquid water, waves, possibly ice at the poles, if the planet has axial tilt and seasons. But descending deeper, the environment would become increasingly alien. On Earth, sunlight penetrates to about 650 feet, 200 meters. This is called the photic zone, where there's enough light for photosynthesis. Below that is the twilight zone, where some light penetrates, but not enough for plants. Below about 3,300 feet, 1,000 meters, is the aphotic zone, total darkness. A deep ocean world would have similar zones, but extending much farther. The photic zone might reach deeper if the water is very clear. The twilight zone might extend for miles. And the aphotic zone, the deep ocean in total darkness, might extend for hundreds of miles downward. In Earth's deep ocean, pressure increases by about 1 atmosphere for every 33 feet, 10 meters of depth. At the bottom of the Mariana Trench, the pressure is about 1,100 atmospheres. That's over 16,000 pounds per square inch. At these pressures, Water behaves differently than it does at the surface. It's denser, more viscous, and has different chemical properties, but it's still liquid. On a super-Earth with an ocean 100 miles deep, the pressure at the bottom would be about 52,000 atmospheres. At this pressure, water can form exotic phases of ice that remain solid, even at temperatures well above water's normal freezing point. These are called high-pressure ices. Ice 7, for example, forms at pressures above about 24,000 atmospheres. It remains solid at temperatures up to several hundred degrees Fahrenheit. On a deep ocean world, you might have a structure like this. At the surface, liquid water in the photic zone, where sunlight allows photosynthesis. Deeper down, liquid water in darkness, where life relies on chemosynthesis or feeding on organic matter falling from above. Deeper still, a transition zone where pressure becomes so high that water starts to behave strangely. And at the bottom, a layer of high-pressure ice separating the liquid ocean from the rocky mantle below. This creates multiple distinct habitats, each with its own challenges and opportunities. Life in the surface ocean would be similar to life in Earth's oceans. Photosynthetic plankton, converting sunlight into organic matter. Small animals feeding on the plankton. Larger predators feeding on the small animals. Complex food webs similar to what we see in Earth's seas. Life in the deep ocean would resemble Earth's deep-sea ecosystems. Organisms adapted to total darkness, high pressure, and cold temperatures. Many would use bioluminescence to communicate or hunt. Some would cluster around hydrothermal vents, where hot mineral-rich water provides chemical energy. Others would feed on organic debris drifting down from the surface layers. But the interface between the liquid ocean and the high-pressure ice layer would be a unique habitat. No equivalent exists on Earth. At this boundary, you'd have liquid water on top and solid ice below, but both at the same temperature. The ice exists because of pressure, not cold. Chemical reactions might occur at this interface that don't happen anywhere else. Certain minerals might dissolve from the ice into the water, providing nutrients. Life might evolve to exploit these specific conditions, creating ecosystems found nowhere else in the universe. And at the very bottom, where the high-pressure ice layer rests on the rocky mantle, you'd have another unique environment. Heat from the planet's interior would flow upward through the rock, warming the base of the ice layer. This might create pockets where the ice melts, forming liquid water in contact with hot rock. Hydrothermal activity could occur here, similar to what happens at Earth's mid-ocean ridges. Superheated water, rich in dissolved minerals, would rise from the rock into the ice or into any liquid water pockets. This would provide chemical energy that life could exploit. Entire ecosystems might exist at the base of the ocean, separated from the surface by miles of liquid water and high-pressure ice. These ecosystems would be completely independent of sunlight, powered entirely by the planet's internal heat. They might be similar to life on Earth in deep-sea vents, or they might be entirely unique. Is this scenario realistic? Scientists think so. Recent studies of ocean worlds in our own solar system suggest that moons like Europa and Enceladus have subsurface oceans with similar structures. Europa, orbiting Jupiter, has an ice shell, about 10 to 15 miles thick, covering an ocean that might be 40 to 100 miles deep. Enceladus, orbiting Saturn, has an ice shell and an ocean of uncertain depth. Both moons show evidence of hydrothermal activity at the ocean floor. Plumes of water vapor, erupting from Enceladus's surface, contain organic molecules and minerals that suggest hot water is reacting with rocks somewhere below. If moons can have these complex ocean structures, super-Earth certainly can. And if life can exist in Europa's or Enceladus's oceans, it can exist in a super-Earth's oceans. The question isn't whether ocean worlds can support life. It's how common they are and whether we can detect life if it's there. Detecting life on an ocean world is challenging. If the ocean is covered by a thick ice shell, like Europa, we might not see any surface features that indicate biology. We'd need to send a probe to drill through the ice and sample the ocean directly. But if the ocean is exposed to space, like we think super-Earth ocean worlds would be, we might detect biosignatures in the atmosphere. Life in the ocean would affect atmospheric chemistry. Photosynthetic organisms would produce oxygen. Decomposition would produce methane and other gases. These gases would dissolve in seawater, and some would escape into the atmosphere. By measuring the atmospheric composition, we could infer what's happening in the ocean below. This is one of the main goals of future exoplanet observations. Find ocean worlds in habitable zones, measure their atmospheres, and look for chemical signatures that suggest biological activity. Ocean worlds might actually be easier to detect life on than Earth-like planets with continents. On Earth, continents weather and absorb atmospheric carbon dioxide. This regulates the climate, but also removes gases that might be biosignatures. On an ocean world with no continents, biosignature gases might accumulate to higher levels in the atmosphere. They might be easier to detect from light years away. This makes ocean worlds prime targets in the search for life. Not because they're more habitable than planets with continents, but because any life they host might be easier to detect. Now we come to one of the most important revelations about super-Earths and habitability. Most of them orbit red dwarf stars, and this changes everything. Red dwarfs, also called M-dwarfs, are the most common type of star in the galaxy. They make up about 75% of all stars. They're smaller and cooler than the Sun, with masses ranging from about 0.08 to 0.6 solar masses. Their surface temperatures range from about 3,800 to 4,800 degrees Fahrenheit, or 2,100 to 2,700 degrees Celsius. Much cooler than the Sun's surface temperature of about 10,000 degrees Fahrenheit, or 5,500 degrees Celsius. Because they're cooler, red dwarfs emit most of their energy in the infrared rather than visible light. If you could see a red dwarf with your eyes, it would glow a dull red, barely brighter than a candle flame from up close. But in infrared wavelengths, it would shine brightly. They're also much dimmer than the Sun in total energy output. The faintest red dwarfs put out only about 0.01% of the Sun's luminosity. Even the brightest red dwarfs are only about 10% as luminous as the Sun. This dimness means their habitable zones are much closer to the star. The habitable zone is the region where a planet receives enough energy to maintain liquid water on its surface. For a red dwarf, with 10% of the Sun's luminosity, the habitable zone would be at about 30 million miles or 48 million kilometers from the star. That's closer than Mercury's orbit around the Sun. For the dimmest red dwarfs, the habitable zone might be only a few million miles from the star. Planets would orbit their stars in a matter of days rather than months or years. At these close distances, something interesting happens to the planets. They become tidally locked. Tidal locking is the same phenomenon that keeps the Moon showing only one face to Earth. The Moon rotates on its axis at exactly the same rate it orbits Earth. 1 lunar day equals 1 lunar orbit, about 27.3 Earth days. So the same side of the Moon always faces Earth, and the far side is never visible from our planet. This happened because Earth's gravity created tidal bulges in the Moon's structure. The Moon isn't a perfect sphere. Earth's gravity pulls more strongly on the side facing us than on the far side. This creates a slight elongation, a bulge pointing toward Earth. As the Moon rotated faster than it orbited in the distant past, this bulge moved around the Moon. But moving the bulge requires energy because you're fighting against Earth's gravitational pull. This energy comes from the Moon's rotation. Over millions of years, the tidal interaction slowed the Moon's rotation until the bulge became locked, pointing toward Earth. At that point, the rotation rate matched the orbital rate, and the tidal locking was complete. The same process happens to planets orbiting close to their stars. The star's gravity creates tidal bulges on the planet. These bulges dissipate energy through friction, slowing the planet's rotation. Eventually, the planet becomes tidally locked with one hemisphere permanently facing the star and the other in perpetual darkness. For planets in the habitable zones of red dwarfs, tidal locking happens relatively quickly. The timescale depends on the planet's distance from the star, its size, and its internal structure. But for most habitable zone, planets around red dwarfs, tidal locking occurs within a few 100 million to a few billion years. This is fast enough that virtually all such planets are tidally locked today. They've had billions of years to reach this state. When astronomers first realized this, it seemed like a catastrophic problem for habitability. Imagine a world where one side is in eternal day and the other in eternal night. The day side would be scorched by constant starlight. With no night to cool down, temperatures would soar. The oceans on the day side might boil away. The night side would be in permanent darkness, receiving no energy from the star. Temperatures would plummet far below freezing. Any water would freeze solid. Eventually, the entire atmosphere might freeze out onto the night side, leaving the day side airless and the night side covered in frozen air. The planet would be uninhabitable. Only a narrow ring at the terminator, the boundary between day and night, might have moderate temperatures. But this ring would experience constant hurricane-force winds as hot air from the day side rushed toward the cold night side. Permanent storms raging around the planet's circumference. This scenario seemed to rule out tidally locked planets as candidates for life. But then, scientists started running detailed climate models. They built computer simulations of tidally locked planets, inputting realistic parameters for atmospheric composition, planetary size, and stellar energy. The models calculated how air and ocean currents would flow, how heat would be transported, and what temperature patterns would emerge. The results were surprising. Even with a relatively thin atmosphere, similar to Earth's or somewhat thinner, heat transport from day to night is efficient enough to prevent the worst-case scenarios. Here's how it works. Air, on the day side, heats up and rises. Hot air is less dense than cold air, so it floats upward, creating a region of low pressure at the surface. This rising air flows at high altitude toward the night side. As it moves away from the star, it gradually cools. Eventually, it sinks back down toward the surface on the night side. At the surface, the cold air flows back toward the day side to replace the air that's rising there. This creates a stable circulation pattern, a convection cell spanning the entire planet. Hot air rises on the day side, flows to the night side at high altitude, sinks, and returns at the surface, continuously moving heat from the day side to the night side. The simulations showed that this circulation is vigorous enough to keep the night side from freezing. The temperature difference between day and night might be significant. Perhaps 50 to 100 degrees Fahrenheit or 27 to 55 degrees Celsius or more. But both sides would remain above the freezing point of water. Depending on the atmospheric thickness and composition, night-side temperatures might be around 30 to 50 degrees Fahrenheit or -1 to 10 degrees Celsius. Cool, but not frozen. Day-side temperatures might be around 80 to 130 degrees Fahrenheit or 26 to 54 degrees Celsius. Warm, but not boiling. The subsolar point, the spot directly under the star, would be the hottest location. But even there, the temperature wouldn't be extreme. Thick cloud cover would form as warm, moist air rises and cools. These clouds would reflect much of the incoming starlight back into space. This is a negative feedback loop. More heat leads to more clouds. More clouds reflect more light. Less light reaches the surface. Surface heating decreases. This prevents runaway heating and keeps the day side habitable. Beneath the clouds, conditions might be hot and humid, but not uninhabitable, like a tropical rainforest on Earth. High temperatures, high humidity, frequent rain, but full of life. The Terminator region, the boundary between day and night, would experience interesting weather. This is where warm air from the day side meets cool air from the night side. The temperature gradient drives strong winds, but these winds wouldn't be chaotic hurricanes. They would be steady, predictable flows, like Earth's trade winds, but stronger and more consistent. Because the planet doesn't rotate relative to the star, the wind patterns don't shift. They're permanent features, always blowing in the same directions. Life could adapt to these constant conditions. Plants, or their alien equivalents, might evolve stems that bend permanently in one direction, shaped by the endless wind. Animals might use the winds for migration, gliding on the currents between different climate zones. Flying organisms might live their entire lives in the air, riding the perpetual winds around the planet. The climate models also showed something unexpected. Tidal locking might actually create more stable conditions than Earth has. On Earth, the planet's rotation creates day-night cycles that drive temperature variations. During the day, the ground heats up. During the night, it cools down. This daily cycle affects weather, ocean currents, and biological rhythms. Earth also has seasonal variations due to its tilted axis. As Earth orbits the Sun, different hemispheres tilt toward or away from the Sun. This creates summer and winter, driving annual temperature cycles, and over longer timescales, Earth's orbit varies slightly. The Milankovitch cycles, variations in orbital eccentricity, axial tilt, and precession, cause climate changes on timescales of tens of thousands to hundreds of thousands of years. These cycles have driven ice ages and warm periods throughout Earth's history. Life on Earth has had to adapt to all these variations. Daily temperature swings, seasonal changes, and long-term climate shifts. This requires flexibility, the ability to tolerate a range of conditions. Specialists, organisms adapted to very specific conditions, often struggle when the environment changes. Generalists, organisms that can tolerate many conditions, tend to survive better. A tidally locked planet wouldn't have these variations. Its orientation to its star is fixed. The day side is always hot, the night side always cold, the Terminator always moderate. No daily cycles, no seasonal changes, no Milankovitch variations. The climate is stable over millions or billions of years. Life on such a planet could become highly specialized. Organisms on the day side could be perfectly adapted to constant warmth and sunlight. No need to tolerate cold, because cold never comes. Organisms on the night side could be perfectly adapted to darkness and moderate cold. No need to tolerate heat or bright light. Organisms in the Terminator could be perfectly adapted to steady winds and moderate temperatures. Each ecological zone would be stable over geological timescales. Evolution could produce organisms exquisitely optimized for their specific environments. This might lead to greater biodiversity, not less. On Earth, climate variations limit how specialized organisms can be. On a tidally locked super-Earth, the sky's the limit for specialization. Each climate zone might develop ecosystems as complex as Earth's entire biosphere. Of course, this is speculative. We won't know what life on tidally locked planets actually looks like until we find some and study it. But the principle is sound. Stability allows specialization, and specialization can lead to complexity. There's one more advantage to tidally locked planets that deserves mention. The permanent day side allows continuous photosynthesis. On Earth, plants photosynthesize during the day and respire at night. They produce sugar from sunlight and carbon dioxide during the day. They burn that sugar for energy at night. This day-night cycle is inefficient. Half the time, plants aren't photosynthesizing. On the day side of a tidally locked planet, photosynthesis could be continuous. Plants could produce energy 24/7, 365 days a year. This might allow them to grow faster, produce more biomass, and support larger herbivore populations. The day side could be extraordinarily productive. Dense forests, or their alien equivalents, covering vast areas. Herbivores, grazing constantly on the abundant plant life. Predators, hunting the herbivores. An ecosystem of incredible richness, powered by endless sunlight. The night side, meanwhile, could host ecosystems powered by chemosynthesis. Just as life exists around Earth's deep-sea hydrothermal vents without any sunlight, life on the night side could thrive on chemical energy. Volcanic vents on the surface, hot springs, geothermal areas, all could support life. Bacteria converting chemical energy into organic matter. Larger organisms feeding on the bacteria. Complex food webs independent of sunlight. The two hemispheres might develop completely different biospheres. One powered by light, one powered by chemistry. Connected only by organisms that migrate between them or by nutrients transported by rivers and ocean currents. This division might actually promote biodiversity. Two completely different energy sources, two completely different selective pressures, two independent evolutionary histories. Like Earth's landmasses, isolated by oceans, evolving separate ecosystems, but on a much grander scale. With all this understanding in place, let's explore the actual super-Earths we've discovered that could harbor life. The first one takes us back to where our search for Earth-like worlds really began. The result will be images sharp enough to separate a planet's light from its star's light, even for planets in relatively close orbits. Super-Earths in the habitable zones of nearby red dwarfs will be prime targets. The telescope will capture direct images, then analyze the reflected light spectroscopically. Different surface materials reflect light differently. Oceans reflect strongly in blue wavelengths. Vegetation reflects strongly in near-infrared wavelengths, creating a feature called the red edge. Ice and snow reflect across many wavelengths, but with specific absorption features. By analyzing the spectrum of reflected light, astronomers can map the planet's surface. They can distinguish between ocean, land, ice, and possibly vegetation. They can detect clouds and weather patterns. They can watch seasonal changes as the planet orbits its star. All of this from dozens of light years away. Beyond ground-based telescopes, space missions are being planned specifically to find and characterize habitable worlds. The Habitable Worlds Observatory is a proposed space telescope that would be optimized for this task. Current plans suggest a launch in the 2040s, though this timeline could change. The telescope would have a large mirror, possibly 6.5 meters or more in diameter. It would observe invisible and ultraviolet wavelengths, where many biosignature gases have their strongest features. It would be equipped with a sophisticated coronagraph to block starlight and reveal faint planets nearby. And it would have spectrographs to analyze the planet's light and determine atmospheric composition. The mission would systematically survey nearby stars, searching for planets in habitable zones. For each detected planet, it would measure the spectrum, looking for biosignature gases. The telescope could potentially find dozens of habitable planets and determine which ones show signs of life. This would transform our understanding of life in the universe. If we found that half of habitable planets show biosignatures, we'd conclude that life emerges readily. If we found that only a few % show biosignatures, we'd conclude that life is rare, even on suitable worlds. Either result would be profound. And if we found technological signatures, radio emissions or atmospheric pollutants suggesting industrial civilization, it would prove we're not alone. Let's talk about what life might actually look like on a super-Earth. This is speculative, but we can make educated guesses based on what we know about biology and planetary conditions. Evolution is remarkably good at solving problems. Given a challenge, life finds a way to adapt. High gravity, stronger skeletons, low oxygen, more efficient respiratory systems, extreme cold, antifreeze proteins in blood, extreme heat, heat shock proteins that protect cells. Life on Earth has adapted to conditions ranging from Antarctic ice to boiling hydrothermal vents. From the crushing pressures of the deep ocean to the near vacuum of high altitude, from pitch darkness to intense UV radiation. If Earth life can adapt to these extremes, super-Earth life can adapt to higher gravity, different atmospheric composition, and tidal locking. First, consider gravity. A super-Earth with twice Earth's mass would have about 40% stronger surface gravity if it has the same density. This is calculated using Newton's law of gravitation. Gravity is proportional to mass divided by radius squared. If you double the mass and increase the radius by about 26%, which is typical for a rocky planet, you get about 40% more surface gravity. On Earth, we measure gravity as 1g. On a super-Earth, it might be 1.4 g. That doesn't sound like much, but it would have profound effects on life. Consider the energy required to move. Walking requires lifting your legs against gravity with each step. On a 1.4 g world, each step would require 40% more energy. Over a lifetime. That adds up. Animals would evolve to minimize unnecessary movement. They might be less active than Earth animals, moving only when necessary. Or they might evolve more efficient locomotion systems. Jumping would be much harder. On Earth, a human can jump about 1 to 2 feet vertically. On a 1.4 g world, the same muscle power would lift you only about 70% as high. Animals that rely on jumping, like frogs or kangaroos, would need much stronger leg muscles. Or they might evolve different strategies, perhaps climbing or swimming instead of jumping. Flying would be affected too. Birds generate lift by forcing air downward with their wings. The amount of lift depends on air density and wing surface area. In higher gravity, flying creatures would need larger wings relative to their body mass. Or they might need denser atmospheres to provide more lift. Super-Earths often have thicker atmospheres, which would help. The denser air would make flying easier, despite the higher gravity. But it would also create more drag, requiring more power to fly fast. The result might be flying creatures with large wings, strong flight muscles, and relatively slow flight speeds. Gliding might be more common than active flight. Large membranes for catching air currents, minimal flapping, skeletal structure would be crucial. Bones need to support body weight against gravity. On Earth, the largest land animals have reached the limits of what bone can support. Elephants weigh about 6 tons and have incredibly thick leg bones. Sauropod dinosaurs like Argentinosaurus weighed over 70 tons and had specialized bone structures with air pockets to reduce weight while maintaining strength. There's a theoretical maximum size for land animals based on bone strength and gravity. On a higher gravity world, this maximum would be lower. Land animals would be smaller and stockier. Their legs would be thicker relative to their body size. Their bones would be denser. They might have more legs to distribute weight better. Imagine creatures with 6 or 8 legs, like insects, but scaled up to mammal size. Each leg supporting less weight, allowing the animal to move without overloading any single limb. But aquatic life would face no such constraints. Water provides buoyancy that counteracts gravity. Archimedes' principle states that a submerged object experiences an upward force equal to the weight of the fluid it displaces. This is why you feel lighter in water. On a super-Earth, aquatic animals would still benefit from buoyancy. Higher gravity would affect them less than it affects land animals. We might see aquatic life even larger than Earth's blue whales. Creatures hundreds of feet long, weighing thousands of tons. The ocean would provide the buoyant support they need. Their massive size would be an advantage, allowing them to store more energy, travel greater distances, and dominate their ecosystems. The deep oceans on a super-Earth ocean world would be particularly interesting. With potentially hundreds of miles of water depth, there would be enormous vertical range for life to explore. On Earth, the deep ocean is divided into zones based on depth and light penetration. The epipelagic zone, 0 to 650 feet, where sunlight allows photosynthesis. The mesopelagic zone, 650 to 3,300 feet, the twilight zone, with some light but not enough for photosynthesis. The bathypelagic zone, 3,300 to 13,000 feet, total darkness. The abyssopelagic zone, 13,000 to 20,000 feet, near freezing temperatures and crushing pressure. The hadalpelagic zone, below 20,000 feet, the deepest trenches. A super-Earth ocean world might have dozens of such zones, each with distinct conditions, distinct selective pressures, distinct forms of life. Evolution in each zone would proceed independently, creating vast biodiversity. The number of species might far exceed Earth's, simply because there are more distinct habitats. Plant life on a super-Earth would adapt to gravity in interesting ways. Trees on a high-gravity world would face a fundamental challenge. They need to pump water from roots to leaves against gravity. On Earth, tall trees can pump water over 300 feet vertically. They do this using a combination of capillary action and transpiration. Water molecules stick to the walls of tiny tubes in the wood. As water evaporates from leaves, it pulls more water up from the roots through these tubes. It's like sucking water through a straw, but the plant is doing it passively through physical forces. There's a limit to how high this can work. At some point, the weight of the water column breaks the capillary action. Air bubbles form in the tubes, breaking the continuous water chain. This is called cavitation, and it limits tree height. On a higher gravity world, cavitation would occur at lower heights. Trees might max out at 50 to 100 feet instead of the 300 feet that giant sequoias reach on Earth. But plants would find other strategies. Instead of growing tall, they might grow wide. Forest canopies might be low and broad, creating dense coverage close to the ground, or plants might abandon the tree strategy entirely. Imagine forests of giant ferns or mosses growing in thick mats that cover the landscape. Each individual plant small, but collectively forming a vast photosynthetic surface. Vines might be more common than standalone trees. They could grow along the ground or climb rocks without needing to support their own vertical structure. This would allow them to spread widely while avoiding the challenges of tall growth. The composition of the atmosphere would profoundly affect respiration. On Earth, the atmosphere is about 78% nitrogen, 21% oxygen, and 1% argon and other gases. This composition allows animals to extract oxygen efficiently, but super-Earths might have different atmospheric compositions. Some might have more carbon dioxide left over from volcanic outgassing. Some might have more water vapor if they're ocean worlds. Some might have less oxygen if photosynthetic life hasn't been around as long or is less productive. Life would adapt to whatever is available. If oxygen levels are lower, animals might have larger lungs relative to body size, or more efficient oxygen-binding proteins in their blood. On Earth, hemoglobin binds oxygen and transports it to cells. Some organisms use hemocyanin instead, which is less efficient but works in certain conditions. On a super-Earth with unusual atmospheric chemistry, life might evolve entirely different oxygen transport systems, perhaps proteins using different metal ions to bind oxygen, or different gas exchange surfaces optimized for the available gas concentrations. If the atmosphere is thicker, as many super-Earths would be, the partial pressure of oxygen might be higher, even if the percentage is lower. Partial pressure is what matters for respiration, not percentage. It's the actual amount of oxygen molecules available, not the ratio to other gases. A thicker atmosphere with 10% oxygen might provide more oxygen molecules than Earth's thinner atmosphere with 21%. In that case, life might thrive despite the lower percentage. Metabolic rates might be different too. On Earth, warm-blooded animals maintain constant body temperature by burning calories. This requires a lot of energy. In a thicker atmosphere or on a planet with more stable temperatures, maintaining body temperature might require less energy. Animals could afford to be less efficient metabolically. Or they might use the extra energy for other purposes, like larger brains or more active lifestyles. Intelligence could evolve along different paths. On Earth, intelligence evolved in several lineages: primates, including humans, cetaceans, dolphins, and whales, corvids, crows and ravens, parrots, cephalopods, octopuses, and cuttlefish. Each evolved intelligence independently to solve different problems. Primates use tools and social cooperation to find food and avoid predators. Cetaceans use complex communication to coordinate hunting in three-dimensional ocean environments. Corvids use problem-solving to access food in difficult locations. Cephalopods use camouflage and behavioral flexibility to hunt and hide. On a super-Earth, similar selective pressures would favor intelligence. Complex environments, social interactions, predation, competition, all drive cognitive evolution. But the specific forms intelligence takes might be very different. An intelligent species adapted to high gravity might be low to the ground, possibly with many limbs. An intelligent aquatic species might have echolocation far more sophisticated than dolphins. An intelligent flying species might navigate using magnetic fields or polarized light. Tool use might evolve differently if materials are scarce or difficult to manipulate. Perhaps biological engineering, breeding organisms for specific purposes, would replace mechanical tools. Or chemical engineering, using naturally occurring substances to create materials and medicines. Language could evolve in many forms. Vocalizations like human speech. Bioluminescent patterns like some deep-sea creatures. Chemical signals like ants and bees. Complex gestures like sign language. Any communication system complex enough to convey abstract concepts could support culture and technology. And once you have culture and technology, you have the potential for civilization. On a tidally locked super-Earth, civilizations might emerge on the day side, the night side, or the Terminator. Each location would shape the civilization differently. A dayside civilization would have constant sunlight. Agriculture would be continuous, with no seasons to work around. Energy would be abundant from solar collection, but they'd need to deal with constant heat and possibly constant storms at the subsolar point. A night-side civilization would develop in perpetual darkness. They might never develop astronomy in the same way we did, since they can't see stars. Their technology might focus on artificial light, geothermal energy, and underground living. They might be entirely unaware of the day side until they develop the capability to travel there. A Terminator civilization would experience steady winds, moderate temperatures, and a sun fixed on the horizon. Their architecture might be oriented around wind patterns. Their energy systems might harness the constant airflow. They might develop sophisticated understanding of fluid dynamics earlier than we did. Each of these civilizations would have unique perspectives on the universe. Their science, philosophy, and culture would be shaped by their environment. And if we ever make contact, we'll learn just how different intelligent life can be when it evolves under different conditions. If the planet is tidally locked, life would face unique challenges and opportunities. On the permanent day side, organisms would need to protect themselves from constant sunlight. They might develop reflective surfaces to avoid overheating. They might spend much of their time underground, emerging only during dust storms that temporarily block the sun. They might be nocturnal by our standards, most active during the brief periods when clouds provide shade. On the permanent night side, life would need to survive without photosynthesis. But chemosynthesis, using chemical energy instead of sunlight, could support ecosystems. On Earth, life exists in the deep ocean and deep underground, thriving on chemical energy from geological processes. Similar life could dominate the night side of a tidally locked planet. Ecosystems might cluster around volcanic vents, where hot, mineral-rich water provides both warmth and chemical energy. Bacteria would convert the chemical energy into organic matter. Larger organisms would feed on these bacteria. Predators would hunt the herbivores. An entire food chain powered by the planet's internal heat rather than starlight. The twilight zone, the boundary between day and night, might be the most biologically diverse region. It would receive moderate amounts of sunlight, allowing photosynthesis, but without the intensity of the subsolar point. Temperatures would be moderate, not too hot, not too cold, and there would be strong, persistent winds as air circulates between the day and night sides. These winds could be harnessed by flying organisms. Imagine ecosystems of aerial plankton, tiny organisms drifting on the perpetual winds. Larger flying creatures would feed on this plankton, swooping through the air currents. Predators would hunt the herbivores in three-dimensional aerial chases. The twilight zone might host the most complex and active ecosystems on the planet. Intelligence could evolve in any of these environments. On Earth, intelligence has evolved multiple times independently. Dolphins and whales are highly intelligent despite being entirely aquatic. Octopuses are highly intelligent despite having completely different nervous systems from vertebrates. Crows and parrots show remarkable problem-solving abilities. Even some insects show signs of complex cognitive processing. Intelligence is not limited to land-dwelling mammals. It can emerge in oceans, in the air, in trees, anywhere that complex challenges favor cognitive solutions. On a super-Earth, we might find intelligent life adapted to their environment. Aquatic intelligence in the deep oceans, communicating through sound and bioluminescence. Flying intelligence in the twilight zone, navigating three-dimensional space and cooperating in aerial hunts. Underground intelligence on the night side, building tunnels and chambers lit by bioluminescent fungi. Each would be as sophisticated as human intelligence, but expressed in completely different ways. And if technological civilization emerged, it would look different from human civilization. An aquatic species couldn't use fire, which was crucial to human technological development, but they might develop other technologies. Selective breeding of useful organisms, construction using coral or volcanic rock, manipulation of ocean currents and thermal gradients for energy. Eventually, they might discover principles of physics and chemistry. They might develop tools and machines adapted to underwater use. They might even develop space travel, though the challenges would be different from what humans faced. The point is that life on super-Earths would be adapted to conditions we can barely imagine, but it would still be life, subject to the same evolutionary pressures, following the same basic principles. And somewhere among the billions of super-Earths in the galaxy, some of this life has probably evolved intelligence. Civilizations that look up at their skies and wonder if they're alone, just as we do. Let's step back and consider what all of this means. The search for habitable planets has revealed something profound about our assumptions. We thought Earth was the template. We thought the best place for life would be a planet almost identical to our own. But the universe has shown us we were thinking too small. The galaxy's most common, potentially habitable worlds are larger than Earth. They orbit stars, smaller and cooler than the Sun. Many are tidally locked with permanent day and night sides. Some are covered entirely by oceans, hundreds of miles deep. These differences aren't flaws. They're features that might make these worlds even more suitable for life than Earth. Stronger gravity provides better atmospheric retention. More internal heat drives vigorous geology and longer-lasting magnetic fields. Tidal locking creates stable climate patterns that persist for billions of years. Large oceans provide vast volumes for life to inhabit. And the stars these planets orbit will shine for hundreds of billions of years, giving life essentially unlimited time to evolve. The statistical implications are staggering. If 30 to 50% of red dwarfs have potentially habitable super-Earths, and red dwarfs make up 75% of all stars, then habitable planets might outnumber stars in the galaxy. Current estimates suggest there are about 200 billion to 400 billion stars in the Milky Way. About 75% of these are red dwarfs. That's roughly 150 billion to 300 billion red dwarf stars. If 40% of red dwarfs have at least one planet in the habitable zone, that gives us 60 billion to 120 billion potentially habitable planets, just around red dwarfs in our galaxy alone. Not all of these will be super-Earths, and not all will actually be habitable. Many will be too massive, or have the wrong atmospheric composition, or suffer from stellar flares. But even if only 1% of these planets actually host life, that's 600 million to 1.2 billion inhabited worlds in the Milky Way. The universe contains about 2 trillion galaxies. If the Milky Way is typical, then the universe might contain on the order of 10 to the power of 20 planets with life. That's 100 quintillion living worlds. The number is so large, it becomes almost meaningless. But it suggests that life is not rare. Life is probably common, possibly ubiquitous throughout the cosmos. We just haven't found it yet, because the distances are so vast and our detection methods are still crude. This statistical argument doesn't prove that life exists elsewhere. It's possible that life is far more difficult to start than we think. It's possible that some unknown barrier prevents it from arising, even on otherwise perfect planets. But the sheer number of opportunities makes it seem unlikely that Earth is unique. Somewhere among those 100 quintillion worlds, life has probably emerged, evolved, and possibly become intelligent. The search for that life is one of the great quests of our time. And now we know where to focus our attention. Not on sun-like stars, though we'll certainly keep studying them, but on red dwarfs and their super-Earths, the most common, potentially habitable worlds in the galaxy. The implications extend beyond science. If we confirm that life exists on other worlds, it changes our philosophical understanding of our place in the universe. We're not alone. We're not unique. We're one expression of a cosmic phenomenon that occurs wherever conditions permit. This realization could be humbling. We're not special, not the center of creation, not the universe's only conscious observers. But it could also be empowering. We're part of something larger, connected to other living worlds across the galaxy. And if intelligence is common, we might eventually make contact with other civilizations. Not in our lifetimes, probably. The distances are too vast for easy communication. But future generations might detect signals from alien technology. They might receive messages sent across the light years. They might even establish dialogue, exchanging information and ideas with beings who evolved under different stars. That future is possible. Not certain, but possible. And the first step toward that future is finding habitable super-Earths and determining if they actually host life. We're living at a remarkable moment in history. For all of human existence, we've wondered if we're alone. We've looked up at the stars and speculated about other worlds. We've imagined alien life in countless forms. But we've never had the tools to actually find out. Now we do. The telescopes exist or are being built. The detection methods work. The theoretical understanding is in place. Within our lifetimes, or shortly thereafter, we might finally answer the question that has haunted humanity since we first became conscious. Are we alone? And the answer is likely to be no. The universe is full of life. It's full of super-Earths, orbiting red dwarfs, worlds where evolution has had billions of years to create complexity. Some of those worlds host simple microbes. Some host complex ecosystems. Some might host intelligence. And finding them, studying them, learning from them will be one of the greatest achievements in human history. The search for habitable super-Earths is more than a scientific endeavor. It's a quest to understand who we are and whether we're alone. It's a journey to expand our perspective and see ourselves as part of a larger cosmic community. And it's a recognition that the universe is more wonderful, more diverse, and more full of possibility than we ever imagined. For thousands of years, Earth was all we knew. Our planet, our star, our solar system. We assumed they were the norm, the template, the best possible configuration for life. But the universe has revealed a different truth. Earth is one possibility among many. A small, relatively low-mass planet orbiting a medium-sized yellow star. Conditions here happened to be suitable for life, and life emerged and evolved. But Earth is not the optimal configuration. It's not the best place the universe can create for biology. That distinction belongs to the super-Earths, larger, with stronger gravity that holds atmospheres tighter, with more internal heat that drives vigorous geology and long-lasting magnetic fields, orbiting stars that live hundreds of times longer than the Sun. Worlds where evolution has more time, more space, more stability to experiment. These are the planets where life has the best chance not just to emerge, but to thrive, to develop complexity, to produce ecosystems more diverse than Earth's, to potentially give rise to intelligence and civilization. The most habitable planets in the universe aren't copies of Earth. They're super-Earths. And they're waiting for us to find them.